Good morning, everybody. I was asked to explain the deviation of real gases from ideal gases. Now, if you go to your textbook on page 118, they describe some very important properties of the ideal gas. Number one is something about the particles being identical in every way. Number two says that the particles has no volume. So that tells you something about an ideal gas, that it is an hypothetical gas, because real gases do have volume. So the particles actually takes up some space, where if you have a container filled with the hypothetical ideal gas, you can't even put a dot for these ideal gas particles, because that would occupy some space. But a real gas, the particles actually takes up some space. That's the first very important thing. Secondly, there are forces of attraction. And repulsion. Between real gas particles, where for an ideal gas there are no forces, whether attraction or repulsion. And thirdly, the important thing is the collisions are elastic. Elastic collisions means that no energy is lost. When the particles collide, where here the ideal gas, the third point is that the collisions are inelastic. So it means that energy is lost. During a collision. Next, I would like to look at the ideal gas laws. There are three of them. The first one is Boyle's law. The second one is Charles's law. And the third one is Gay-Lussac. Okay, now Boyle's law, we need to know that if the pressure, the number of moles of the gas is constant and the temperature of the gas, these quantities are constant. the relationship between the pressure and the volume is an inverse proportionality. I'll explain that a little bit later. Charles's law, on the other hand, brings together the volume and the temperature. So here, once again, the moles will be constant and the pressure is constant. So the volume of a gas will be directly proportional to the temperature of the gas. Gay-Lussac, on the other hand, brings the pressure and the temperature into a relationship. So the constant factors here would be the moles and the volume. And the law says that the pressure is directly proportional to the temperature. So where did they get this from? What is the meaning of this? It means that if you make the container bigger, if you increase the volume, so I'm going to symbolize it like this, you increase the space in which the particles can occur, then the pressure will decrease. There will be less collisions. Less collisions means lower pressure. For Charles's law, if you heat up a container, what will happen? The container will expand. So if you increase the temperature, the volume will also increase. Gay-Lussac says that if you have a container and you increase the temperature of the same container, the little gas particles in there will move more vigorously, so the pressure will increase. So if you increase the temperature, the pressure will increase. I have to stop this video here, it's long enough now, and then I'll do another video to carry on.